Hi. In the previous video, we took a look at using Python's standard C types package to access functions stored in compiled C-compatible dynamic libraries, which is a quick way to gain access to functionality that was written in other languages. In this video, we're going to look at a third-party tool called Cython, which is another tool for bridging the gap between Python and software that has been compiled to machine code. If we had a situation that called for us to implement part of our project in compiled code, it would be entirely possible to do it by creating a dynamic library containing the code and call into it with C types. But that's a roundabout way to get where we're going. We'd end up writing a lot of the code twice, once for the sake of our compiler, and then again to tell C types about details, like function signatures and data structures. That's inefficient and violates the don't repeat yourself principle of programming. There's a tool that's better suited to this situation. And as you've surely guessed, that tool is Cython. What Cython does is translate a Python source code file into a C source code file containing the equivalent calls to the Python C API and wrap it in the boilerplate necessary to turn it into a Python binary module. That would be useful enough by itself, but Cython also allows us to interject calls to C functions and low-level data access operations into the module. The end result is that we can pretty much just write our compiled code as if it were Python, and still gain the speed or low-level access that prompted our need to compile. The amount of work this saves us over using the Python CPI API directly is considerable. The 100-line example included with this video translates into more than 5,000 lines of C when it's compiled. Let's go through that example piece by piece and talk about the differences from plain Python. The first thing to note is that in addition to normal imports of Python packages, Cython also allows two additional import mechanisms. The first is called C-import, and what it does is import the signatures of compiled functions and data structures from pre-prepared libraries. In this case, since Cython comes with a pre-prepared library of all of the Python C API functions, we're able to use that mechanism to import the needed information about Python's low-level memory allocation and deallocation functions. The second additional importing mechanism is cdef extern from. When we don't already have the signature of a compiled function available, we use the syntax to make it available in the Cython code. The indented block can contain any number of function declarations, type defs, structure definitions, and so on. But they don't have to be precisely correct, just close enough that Cython is able to generate proper C code. A cdef extern from block references a C header file, which is automatically included in the generated C code. While we could simply use the normal Python syntax for the class statement, prepending it with a cdef gives the ability to store raw data values in predefined variable members of the class instances. The num values variable, for example, is just a chunk of memory storing the bits that represent an integer value. It doesn't have any of the extra data needed to turn it into a Python object. This is a bad thing in a way because it means that Python can't do any of the smart things it does to help us write good code quickly. But we wouldn't be working with these tools if we didn't have a reason to do some of that work for ourselves. So here, we're defining an extension type called statistical array, which contains a pointer to a memory location and two integers. The memory location is supposed to contain double precision floating point numbers. These are raw machine-level values, and while primitive in comparison to Python values, they're very fast because they can be fed directly into CPU operations. Here, we have the functions that set up and dispose of instances of the statistical array class. Notice that the setup function is called cinit, not init. Actually, a Cython CDEF class can have both. The cinit function's job is to set up the raw variables for the class instance. And the normal init function is supposed to set up any normal Python variables it contains. The cinit function is called first, and it's not guaranteed that self will actually be a valid Python object itself yet. So it should confine itself only to initializing the raw variables. The reason cinit accepts the extra positional and keyword arguments is so that if a Python class inherits from our class and adds more parameters to the signature of init, the cinit function will still work. At the other end of the process, we have the dalloc function, which needs to release any specially allocated resources associated with the class instance. In this case, we allocated a chunk of memory in cinit, so we need to release that memory here. Now here, we're defining a few of Python's normal magic methods, allowing us to iterate over the values stored in our object and access them by indexing. The thing to notice here is how little has changed from what we'd be doing in a pure Python implementation. The only real differences are the type definitions we provided for every parameter and local variable. We didn't actually have to do even that, but it lets Cython generate planned C code for a lot of the operations we're performing, which means we're using the CPU directly instead of the Python virtual machine. We're trading flexibility for speed. The previous functions were all defined with the def keyword, as normal for Python, and the functions created operate as if they had been defined in a normal Python module. Cython gives us two other options, though. Instead of def, we can use cdef, in which case the function is much faster to call, but is only for use by other Cython code. This is great for internal help functions and such. Or we can use cpdef, in which case the function is accessible from normal Python, but is almost as fast as a cdef function when called from Cython code. We've chosen cpdef here because we want to expose the full feature set to any Python code that uses our compiled module, but we also expect to use the same functionality from within our Cython code. Here, we're getting to the reason we called our class a statistical array. We're implementing several discrete statistical calculations using the values stored in the class instance. You don't have to care what mean, variance, and covariance actually do, but let's take a look at how they do it. In the mean function here, we see a loop that calculates the sum of the values stored in the array. If we were running that code in Python, each cycle through the loop would involve several dictionary lookups and function calls. In the code that Cython generates, it's 4 lines of C code that translates into only a few machine code operations. That's possible because we told Cython that the index variable should be a C integer. And because Cython is smart about handling loops with C integer variables, we gain a similar benefit in the variance and covariance functions. Again, we just use Python syntax and give Cython additional information that it can use to optimize the generated code. There is one unusual thing to note with covariance, though. At the end of the first line, we see except -200.0. What is that? Well, as with most of these functions, we gave the covariance function an explicit C return type of double. That's a big gain in terms of speed, when the code call in the function is also Cython and stores the return value in a cdef double variable. But there's a downside. Normally, Cython would use the return value to signal that an exception has been raised. But how's it supposed to do that when we change the return type and it doesn't know which values are even valid now? Well, we'll tell it. Adding except -200 means that if the return value is -200, Cython should check to see whether an exception has been raised. If we'd left off the question mark, it would mean that -200 always means there's an exception, which is a bit faster, but we can't go that far because -200 is still a potentially valid return variable. Notice that we don't actually return -200. We just raise an exception as normal. Cython takes care of the rest. Here, we have a couple of functions that are built up using the earlier functions as building blocks. Thanks to our use of cpdef, when we define the variance and covariance functions, there's very little overhead involved in calling those functions from here. Okay, well and good. We've written a somewhat useful Cython class. Now, how do we make it available to Python code? Well, we have to compile it. First of all, that means we need to have a compiler. The documentation on cython.org has a tutorial entry and appendix going through that process. And I suggest referring to them if there's not already a compiler on your system. If we have a compiler, installing Cython is just a matter of asking pip to grab it for us. The install could be a little slow because it needs to do some compiling. During the installation, just be patient while it finishes. Once Cython is installed, we need to create a setup.py describing how to build our extension. For the base case, that's very straightforward. The source code we were working on is saved in statistics and .pyx. Pyx is the standard file name extension for Cython source code files. Once we do that, the last step is a snap. Once the build.ext command is finished, we should have a compiled extension sitting next to our .pyx file. Now all we have to do is import it and use it. Notice that when we cause an exception in the compiled code, the traceback is fully filled in and points us to the cause and location of the problem. That's a Cython feature and a nice advantage. So, we've seen how to use Cython to operate with one foot at Python's high level of abstraction and the other at C's much lower level with surprisingly little pain involved in bridging that gap. We can use that knowledge to optimize bottlenecks in our programs or to access functionality that's only available when we operate close to the hardware. Earlier, we saw how to use C types to access already existing compiled code, making it relatively easy to call on useful features written in other languages. We've come to the end of this course. I hope you've learned a lot and have gained immense knowledge about Python. I loved putting this together for you. Keep learning.